Now I've got two more problems. The first one, the most brief, which is called as planning, and I don't need to tell you that because you've got a powerful technology that gives you a map like this, and it gives you the position of the robot at any point of time. The goal is, so you ask the robot to go to the place where the secretary sits. So I asked the robot using human robot interaction voice on my desktop computer through which I'm recording this lecture. I gave a command to the robot using Wi-Fi, go to secretary. Now, when the robot was being showed everything around, it was also being given annotations that this is where secretary sits. This is where I sit. This is where usually the charger is, or the home, or the origin. This is a very popular place because you get coffee here. So Robert registered all these annotations. So when I say go to secretary, the secretary's coordinates are already known to the robot because I showed the robot the position and it registered this explicitly. So the name of goal to pose of goal. This table is made when the introduction session happens for the robot. Now, of course, the best thing that you can do is to use the A-star algorithm for the deliberative planning. But the problem with the A-star algorithm is that the input to A-star algorithm is a graph. And the graph means that it's discrete. Now, this is a continuous space. So if you want to use a A-star algorithm on continuous spaces, of course, you'll have to discretize it up. Now, previously what we did was we filled in grids like this, and that's the worst thing possible because the grids ask you what is the resolution or the size of the grids. And as a programmer, my problem is I don't know that. Sometimes they are narrow corridors. So I'll inflate all the obstacles by the radius of the robot and it becomes very narrow. So these places need to have extremely fine grids. And that means the entire space I'll fill with these small grids. It'll take a huge time. So if you want to go resolution free, the philosophy is the same that whenever exact algorithm fails, you go with the approximation algorithm. So what you do is you place in random vertices and connect every vertices with the nearest vertices if they are collision free. So like here, if I take the nearest R, so if I take the nearest R for this one, this cannot get added because this has an obstacle in between. So only add the obstacle free ones and you'll get in this kind of roadmap. Why is this better than the A-star algorithm? Because what you do next is that after joining all this thing up, this is offline. So we do this thing when we get the robot. So the first thing that we do is always a slam. The second thing that we do always is make this offline roadmap. It's exactly the same as Google Maps. So of course they use satellite navigation in order to make a map, but then those are heavy algorithms that extract roads from satellite imagery. So they've done that offline and they've converted it to graphs offline. So we had a continuous space, we've converted it into a graph offline. Then we also temporarily add the source and the goal to this roadmap. This is online, so the reds are offline because we could do that as soon as the robot comes. The furnitures don't move, the map does not change, the people move, but they don't constitute a part of the static map. So we do it immediately. We immediately make this red roadmap. Now the problem is that the wherever the robot currently is will not be a part of this red roadmap. That's exactly the same problem when you use satellite navigation to travel. Your home is not a part of the roadmap, so your satellite navigation program tries to connect you to the nearest place which is in the map. You start from a housing society whose data is not available with your satellite navigation. So satellite navigation tries to guess where you are, connects you to the nearest exit. So that's exactly what I'm doing. I'm connecting the robot, which is not at a known position as per the red roadmap. I connect it to the nearest locations, which could be possible exits, and similarly the goal. And then I use my standard graph search algorithm in order to calculate the path. Which is this one. It's better than the A-star algorithm because in A-star algorithm, if I did not get a path, I would have been puzzled. What do I do? So here, if you don't get a path, then you add more vertices and edges. If you don't get a path, you can add more vertices and edges. And let me take an example. So, practical example, that's where my robot is. And of course, this is the door of the robotics laboratory. This is the robotics laboratory, and this is my cabin. And let's take a small robot because the openings are small. I add random vertices and edges. Now, if you see here that I temporarily add, the reds and the blues have been changed. And this was the goal. So I don't get a path from my source to goal. And therefore I say that, okay, I'm not getting a path from source to goal. The master has added, so there's probably a path. Then what I do is I try to intelligently find out at which stage am I not getting a path by my graph search algorithm in this region, and here I add lots and lots of more vertices. That's not what you would have done if you were going with a discrete A-star algorithm. You would have had to increase the resolution of the entire grid. So here I can just add ad hoc vertices and edges. This technique is of course called as the probabilistic roadmap. And into my programming, let's go. So remember, this is the path that I got. Let me make this path explicitly. So the robot just started its life. Using SLAM, it gets to know that this is the map, static map. Then using probabilistic roadmap technique, it knows that this is the path that it should be taking from source to goal. Now we say that, okay, many people come in, so it will break this into sub goals. So let us say the last point visible is this is the sub goal. And as the robot goes around over here, that's my robot. So using potential field, it avoids these people. It goes here. That's still the sub goal. It goes here. It's still the sub goal. And then by the time these people go, so this is navigation using potential field. And this was the fusion of probabilistic roadmap, and probabilistic roadmap is PRM and social potential field. And that's how I go.